It's really important to be able to determine the power absorbed or generated by an electrical circuit element. Remember that as engineers, we need to transfer energy to perform some task. Power is the rate of change of energy, so power and energy are very closely related. Regardless of what type of system we're talking about, power is defined as the rate of change of energy transfer, or equivalently, the rate at which work is being done. For electrical systems, voltage is an energy difference a charge has at two different points. Another way to look at this is that voltage is the work done in moving a charge from one point to another. Current is the rate at which charge is moving between 2 points. Therefore, electrical power is the product of voltage and current. This is the rate at which work is being done by moving charges from one voltage level to another. The units of power are watts, which are joules per second. Electrical circuit elements can either absorb or generate power. If an element absorbs power, it's converting electrical energy to some non-electrical form. Resistors, for example, convert electrical energy to heat. They always absorb power. If an element generates power, it's converting non-electrical energy to electricity. A battery, for example, will typically generate power by performing a chemical reaction to provide electrical energy to a circuit. Be careful, though, when determining whether an element is absorbing or generating energy. A battery can absorb electrical power. That's exactly what's happening when we charge a battery. Next, we'll see how to use the relative signs of the voltage and current for an element to determine whether the element is absorbing or generating power. Electrical power is the product of voltage and current for a circuit element. Whether the element is absorbing or generating power can be determined by the sign of the power. If the power is positive, the element is absorbing power. It's converting electrical energy to some other form. If the power is negative, the element's generating power. It's providing electrical energy to the circuit. The passive sign convention determines the relative signs on voltage and current in the power calculation. Recall that in the passive sign convention, the assumed positive current enters the assumed positive voltage terminal. Individually, the sign convention for either voltage or current can be chosen arbitrarily. So probably the most reliable approach to determine power is to choose an arbitrary sign convention according to the passive sign convention. Once you have your sign convention, interpret your actual voltages and currents according to that sign convention. Finally, use the voltages and currents with the signs appropriate for your sign convention to calculate the power. Let's do a couple of examples next to see how this works. For the first example, we have a positive 3 volts across this element, with this being the higher voltage. 2 amps are entering the top terminal. I choose a passive sign convention. Say I choose my positive voltage terminal to be up here. That means positive current has to be entering the positive voltage terminal. This assumed polarity is the same as the actual polarity, so that voltage is positive 3 volts. Likewise, this assumed current direction is the same as this direction, so I is equal to positive 2 amps, and the power is 3 volts times 2 amps, which is 6 watts. So this element is absorbing 6 watts of electrical energy. My result here doesn't depend on what sign convention I use. If I assume that this is my positive voltage terminal, that means that this will be positive current direction, since current has to enter the positive voltage terminal. So this assumed polarity is the opposite of the actual polarity, so V has to change sign, and V becomes negative 3 volts. This assumed current direction is opposite of the actual direction, so I has to change signs as well. It's negative 2 amps. So power is negative 3 volts times negative 2 amps, and it's still positive 6 watts. Next problem is here. I have positive 3 volts with this polarity, so this voltage is 3 volts higher than this voltage. 1 amp is entering this terminal. I'll choose an arbitrary current direction. Say this is my positive current. That means this is my positive voltage polarity. Positive current enters the positive voltage terminal. This assumed polarity on voltage is the opposite of the actual polarity, so I have to change signs on the voltage value. So V is equal to negative 3 volts. My assumed current direction is the same as the actual direction, so I does not need to change sign. It's positive 1 amps, and power is equal to negative 3 volts times 1 amp, or negative 3 watts. This element is generating power. Finally, I have negative 2 amps going this direction. I'm going to choose this to be my positive current direction. That means that this has to be my voltage polarity. Positive current enters the positive voltage terminal regardless of the actual polarities and current directions. This current is the same direction as this, so I is minus 2 amps. This voltage polarity is the opposite of the actual polarity, so I have to change sign on the voltage. So V is equal to negative 5 volts. And power is negative 2 amps times negative 5 volts, which is positive 10 watts. Finally, let's take a look at the principle of conservation of power. Conservation of power simply states that in any electrical circuit, the total power absorbed is balanced by the total power generated. This fact can be very useful for double-checking results of analyses and measurements. An alternate way of stating the law of conservation of power is that the algebraic sum of all the power in the circuit must be 0. Since absorbed power has a positive sign and generated power has a negative sign, we get 0 if the absorbed and generated powers are equal. Let's do a quick example now to see how we can use this in circuit analysis. In this circuit, we know the voltages and currents for elements 1, 2, and this 3 amp source. We want to use conservation of power to find the power absorbed or generated by this voltage source, V sub S. For element 1, the power absorbed or generated by that is based on a sign convention. I'll use plus minus as the sign convention for voltage. That means positive current is in this direction. Both of those sign conventions agree with the actual direction, so I don't need to change any signs. So this is 1 volt times 2 amps, which is positive 2 watts. For the 3 amp source, so P3 amp, I'm going to use a sign convention that is in the same direction as the current. So this is my positive current. That means this is my positive voltage terminal. So 3 amps doesn't need to change its sign. This sign convention is the opposite of this, so I do need to change the sign on the 2 volt difference. So this becomes a minus 6 watts. The power for element 2, I'm going to use this as my positive current direction. It's in the same direction as the actual current, so I'm not going to change signs. That means this is positive and negative. That's the same as the actual sign, so neither of these have to change their signs, and this is 1 amp times 2 volts is equal to positive 2 watts. If I add all of these up, I get negative 2 watts. That has to be balanced out by the power absorbed or generated by V sub S. So PV sub S has to be positive 2 watts in order to make everything sum up to 0, and this voltage source is actually absorbing power. So far, we've just been working with individual circuit elements. We've seen how to choose a sign convention for an element, the voltage-current relationships for a couple of common elements, and the power absorbed or generated by a circuit element. What we haven't done is talk about the interactions between elements. Circuit element interactions are governed by Kirchhoff's voltage law and Kirchhoff's current law, which are the subject of the next 2 videos.